Now, apart from if, we usually use loops. Two kinds of loops you will find in the models I shared with you. For loop and while loop. How for loop works? Like this. For I equal to 0, I higher than n, I plus plus. And I will execute this n times. Okay? Here I am imposing the value to 0, the initial. Init. Then what condition is? I am going to execute if, in case I is below or equal to n. So that will run from 0 to n. And every time I execute, that will be the increment, 1 point, I plus plus. That means 1 point. Okay? So now I execute this n times. 0, 1, 2, 3, n. And an n, I move. Okay? That's the for. If you put one break, like if error t is below max error, whatever, break. Then I forget about this for condition and I jump this. I quit the loop. Remember that we did for y equals 0, I below max number of iterations, I plus plus. And then we started everything, right? We started to explore all the geometry, we started to calculate error and so on. I'm not going to execute all the iterations for every time step. Actually, if I explore maximum number of iterations, it's because something has gone wrong. So now, here, that's why if the error is below a max error, then break. Okay, this break jumps this for. And in the coding that I sent to you, it's like this. It's how I implemented that you are running until you get convergence. You get convergence, move out. Okay? Great. Okay, that was for. While. While is similar to for. When you're here, let's say loops. While loop. You have while condition I below n. I comes with one value, 7. It's 7 below n? Yes, then execute. And usually, at the end of the execution, we say now I plus plus 1.2y. It's similar to for. At the end, you can program using fors or whiles. It's the same. But if it's like a condition, and you now change the condition, so you have, if this condition is this is a boolean, this is an asking. This condition is true or not? It's true, then it gives you 1 point. 1 as value. If it's 1, it goes inside. And it goes inside all the time. Until the condition goes 0. The condition is false. If it's false, boolean value 0, then it jumps and it continues to the code. Okay? Now, okay, print. Print. So we have if, for, while, and printing. Nothing else, I think. This is input output. printf. I'm saying now this, but you can check it always. In this column that is text, if you put 10%, that means it will ask to the value of this variable and the value of this variable. It has this syntax. You copy the syntax. There are printf in the files I share with you. So you just can adapt those and that's it. One thing is printf. Printf means it prints to the console. Like it prints finish in my codes, right? I press, it's black skin, until you get finish. Okay, finish. Or fprintf. Fprintf means file printf. It prints to a file, to a txt file usually. Like all the results we are generating, they are generated here. How I created that? Let's open this case again. Well, maybe with the wall will be easier. That was the case. fprintf. Trans is the communication that you set to the program. Okay, if I'm using the command trans, that means that before the very beginning, I define, okay, I will have file communication. And the file communication is under the name trans. Okay? Now, trans, you need to open and create this txt file, name whatever, and I need to write on that file. Okay. So now the computer knows what trans means. And if I fprintf to that direction, if it's under colon, it's text. Okay, it's time, T0, and those are the labels of the columns. And then I want to put the values. Okay, then fprintf, here in trans, this value, time, f because it's float. Those are float numbers. -n means go other line. Okay? But this is syntax you can figure out in a website, or you can ask me if you have problems. But it's very simple. And that's it. For, while, if, and printing. Or reading from a file. That's it. Nothing else. Okay? So, see help. Done. Now, if I need to debug, if I'm having this, this was the software that we were working with yesterday. This is the wall with two layers. One layer generates heat, the other one it doesn't, and it's transient. Okay, that code we explained yesterday. Imagine we have some problem and we don't know what is going on, and I want to execute line by line my program, because now I say, okay, I execute now, for example, you will say, come on Alvaro, stop repeating this, but you will face this problem. Imagine I have this, if equal to n. But now I execute. It will stay like this. Why? Because it's inside the loop, and I always goes to, when the I value is inside a for loop that say I from 0 to n plus m, I plus plus. Execute this until I is higher than n plus m. N will not be never higher than n plus m, because you have one line inside this loop that is saying I is equal to n all the time. So it goes, it adds 1 point, then again n. And we are inside the loop all the time, forever. So now, wow, it doesn't converge. Why we're not having results? How you solve that? Now it's easy, well, easy, because you have less than 200 lines. But in the water cylinder, let's see how much. Yeah, in this one, we had 1,500 lines. So check a problem here. So, what I recommended to you. If you click on these numbers, you will put like this. You will mark in red the line in which you are clicking. Like, I don't know, this one. That's a breakpoint means. That means that now, instead of executing all the code, I will execute line by line, and I will stop here and see what happens here. To do that is this command, debug, this button, debug. Okay? Or here you have this menu, I don't know how to say it in English, this menu, debug. Okay? So instead of fully execute, like doing this, compile and run, I will debug. Okay, I debug. Hopefully it works, because sometimes the debug of in new computers go bad. Come on. Go bad. Sorry, let me recheck what happens. You have not enabled debugging info -G and in compiler options. Okay, that was because it's the first time I execute the software in this computer, and sometimes we have funny things. It's about compiler options. Okay, let me check. Let's do a 10-minute break, and we'll be back. So we continue a little bit more. Let me tell you again. Okay, so I know what happens now. In the compiler options, the first time you install the software, it's important that you say yes to enable the software to generate debugging information. So this has to be yes, otherwise you cannot debug. To go here, it's Tools, Compiler Options. So you go Tools, Compiler Options, then in Settings, Linker, you have this yes. I will mail you, everybody, because otherwise it will be lost, this info. It's Tools, Compiler Options, Settings, Linker, and then here you said to generate debugging information, yes. Okay, this. Okay. So with this, and now you can debug. So we can circulate through the software line by line. Like, for example, if I press the breakpoint in the line 31, and now I debug, now it stops here, blue line. Blue line means where am I? If I press F7, I advance through the code, line by line. Okay? If you want to see what are the values of certain variables, like usually you want to see how y, t, error, or whatever changes, you add watch. Okay, I want to add the watch of m value, for example. Now it's 0. After executing line number 46, bam, it changes to 10. Everybody follows? I repeat. I repeat? I repeat. Okay. So I will restart again. With these breakpoints, I can mark when I want to stop. Now, if I stop here, and I say debug, I want to not to run the full software, but to run until the breakpoint. And then from the breakpoint, I will press F7 and executing commands one by one. If at any point I want to see what is the value of any variable, I just will add one watch. For example, I debug here, m is 0. You see, here, m value has the value of 0. Until I got F7, 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 F7. You see, in line 46, I assign the value 10 to the variable m, right? Now, after I execute this, now m is 10. Okay. Now, for example, I want to see how much is increment x1. Then increment x1 is 0.005. And because I define it as a float, you saw that the value we were playing with. That is the real value of increment x1. And this is a numerical error. This is a truncation error. Why 1 here? But shit happens. So that's why you need to be careful when you are having a lot of nodes and you are playing with this kind in the limit of the float or the double dimensional decimals. Then you're gonna have these errors which deviate your results. Now it's nothing. Okay. I still execute that. Okay, I execute. Now, initial map of temperature. Okay, I want to see how I value changes. Now, I enter the loop, F7, for I equal to 0. Meanwhile, I is below n plus m, add one value. Okay. Then I want to see what is the initial. It's 25. And I want to see what is the value of temperature IT. Now it's 0. Right? The map of temperature I and T is 0. I also want to watch what is the value of T. I'm at the very beginning of the software. Now I press F7. I impose the value to 25. Is I below n plus m? Yes. Boom. 1 point extra to I. Correct? And execute again. So I will execute this 20 times. This is how the loop works, right? Now it's 21. No. I don't know how much n and m we have. Yeah, 10. So, okay. Okay, I quit this loop. Now we were here. So in this loop, I did this loop 20 times. The 21 say, okay, you're gonna go here inside. Go back. Now, while t is below maximum number of intervals I want to explore. What is the value of t? T is equal to 0. Then it's below number of t. I will check. I will watch number of t. Yeah, 23,000. The condition of the while is okay. Then it will go inside. It will go inside. F7. Now t is equal t plus 1. Now t is equal 0. After the command, t is equal 1. Now I am in the first instant. I want to go from 0 to 1. Okay? Now first thing I want to do is to assume a map of temperatures. Remember, I don't know the map of temperatures in 1, but I needed to calculate all the equations. So my first assumption will be the temperatures from the past. That is this command. And I have to do this command for all the geometry. From I equal to 0 to I equal n plus m. Correct? F7. And the loop will do the work. Now it's 20, 21, it goes out. Have you seen? It did 21, at the value 21, the condition was not okay, it is an enter, it moved. Now, we start the for loop of the iterations. First thing, I reset the error, okay? I reset the error, and now I start with, again, analyzing all the geometry, and for each different node, I will apply the equations I need. Okay? For if I equal to 0, I'm at 0. If I is equal to 0, yes, go inside. It goes inside. And executes the software. Now, temperature, before was 0, now it's 25.0011. Okay? The assumed value of 0t was 25. And the first calculated was 25.001. Okay? We go. Now, I is equal to 0. This if question, it's false. The following. Now I'm asking, is I higher than 0 and below n? No, because it's 0. It would not go in. It doesn't go in. Now, here we have the mistake. Remember? I have forced this mistake. Now I will impose the value of n to y. I press F7. I equal to 10. Why I jump from 0 to 10? If I did a typo, now doing debugging, I say, this is what the mistake. Without debugging, okay? So just to that you fully understand how this works. So we were here. Sorry. Before debugging, you have to compile always. Okay. So you press this button, compile. Because now I changed the software. I added one equal here. So the code was not compiled. I need to compile and then debug or run. Now I can. Okay, I'm here now. Still, I equals 0. Is I equal to n? No. It will not go inside the if. It doesn't. Is I between n and n plus n? No. It doesn't go inside this if. It's equal to n plus n? No, it doesn't go. Okay, I'll calculate the error of that and go back to the loop of geometry. Now I is equal to 1. It will not enter here because it's not I equals 0. It will enter the equations of the I equal 1. And it will advance this way. You see? Now 10 for example. I is equal to 10. Where am I? When I was equal to n, which is 10. So this is one way in which you can guide and see where your model is going. If you think I have some problems in the node at the boundary, you put the breakpoint inside the if, you press, or you think you have, for example, you have a problem at the last node, the node in contact with the air. You don't want to put F7 until you get there. You're now there are 20 nodes, but if you have 1,000, you will play 1,000 loops? No. You go, and if this is running, okay, when you execute line 137, stop. And the algorithm will only execute the value 137 if this condition is on. If this condition is true. Then I debug. I stop here. Now I can watch what value has B, what value has C, what value has the assumed temperature of the following node, what value has all these. If you think you have one problem, you can go to this equation and watch any variable, and if there is some mistake, you can see the root, you can follow the root of this mistake. You can track the root of the problem. Okay? So now, for example, I can see, okay, I can add watch of B value, I can have watch of C value, I can have watch of E, of A, and the temperature that I am assuming for the node, and the temperature that I get as a solution, which is this one. So when I execute all these files, I get B is 500, C is 10, E is 200, A, the addition of all them. B is 500, C is 10. That means that in this case, conduction coming from the west is much more dominant than convection going to the air. Because the heat transfer coefficient is very weak, it's just 10. And the conductivity of the material, if you remember, it was 5 bad meter Kelvin. It was a conductive material So it is more dominant to the state of the node, the conduction, than the convection here. This is some information you can get out of that. Then, when I calculate, I got 25. But this is the first iteration. Okay? Any problem? Questions? Everything is clear? I think this is very useful to do it to the back, always. Never happened to me. I did it correctly at once. Never. Okay? Neither this simple. When I was preparing this for master classes, I also had to the back because some typo happens. As you can see, there is a lot of copy pasting in the coding. So in the copy pasting, you can have some errors sometimes. Yeah? Okay. The back case. Now, last thing for today, probably. Yes. I will show you another paper and then see. Okay, that was the system I used for my PhD. That was a ventilated facade, and it has panels of PCM, of exchange material, in the cavity, in the air channel. Okay, so basically the system here, the numerical model is for cooling purposes. So it was covered, as you can see in the picture. We have the prototype, and the idea was to use, if the temperature during the night was lower than the melting temperature or solidification temperature of the PCM, I got air from outside, I circulate through these cavities, I solidify the PCM, and the following day, before I switch on any cooling device, I get air from the inside, circulate through the cavity, and inject it again to my environment, providing cooling. Okay? So the sketch is like this. So imagine that in the air channel you have a lot of PCM. So you can charge and discharge. At night, there are fans here, you get temperature from the outside, you solidify the PCM. Then you close everything and wait until you need this cooling. When you need this cooling, you get air from the inside, you discharge this cooling, and you put it inside. Okay? I had measurements of that. You saw the prototype. But I wanted to develop a numerical model to analyze several things. First, what happens depending on the weather conditions. I was able to test this only in Lleida. But in Lleida, summers are tough, meaning that temperatures at night hardly ever drops below 20. And the PCM that we were using here melts around 22. So I need cooling at night to solidify that, otherwise it's not solid. Okay, we tested experimentally in Lleida and it doesn't work in Lleida. It means that the electricity I needed to run the fans was higher than the electricity saved by the heat pump. Okay, in my PhD, the system for cooling, it doesn't work. I developed the numerical model, so I can say, okay, what happens if I operate the fans accordingly, properly, in a smart way? What happens if I change the PCM? What happens if I change the weather conditions? Maybe in Lleida doesn't work, but in Germany it does. I don't know. So that's why numerical modeling is very useful. Okay? So how I did that? The geometry is very challenging. You have the panels like this. Those are PCM panels. And the air flows like that. So the modeling was, it also included, it was like this. So I assume that all the plates behave the same. I had 14 plates this way, but why should one plate behave differently than the other? If they are exposed to the same conditions, I just need to model one plate. Okay? One plate. But in this case, so this plate will behave exactly the same as this one. meaning that this temperature is the same as this one, right? And this is the same as this one. Okay, and then there is one air node, which is the same temperature. Here we have different physics that we were observing. The different physics is, or the other physics that we are added is thermal radiation between surfaces. Because it happens that you have, like this is brick, this is the insulation that is covered to the outer skin. So this surface is at one temperature, this surface is another temperature, this is another, and this is another. In a closed environment, they exchange thermal radiation between them. I cannot say we have only conduction and convection from the air to the surface. No, but also between surfaces, they were thermal radiation. Okay, that's something you have to take into account when you are doing the energy balance of this node, of this node, of this node, and this node. Right? But this is a 2D model. Because there are differences in this direction, let's say, and in this direction. But that's it. I mean, each wall, this wall doesn't have variation in this direction. What I did is, I have brick, sorry. Starting, how to convert this is a 3D. Of course, it's a 3D. I converted to a 2D. How? This is node I equals 0. N nodes. I equal N. For example, right? This is node, the air, I equal M plus 1. This is node, I equal M plus 2. This is node, I equal to M plus 2. This is node, I equal M plus 3. I equal M plus P plus 3. In this way, one single vector explored me all the geometry. I didn't need to increase another dimension. Why? The same vector is going this direction, then this direction, then the air, then this direction. Okay. The three different solids that I have, insulation, brick, and PCM, were crossed by the same. And then I have J, which is in this direction, like in the vertical of the facade. But this is another example on how we can, the facade behaves as a 3D, yes. But can we assume that? Yes, because there are no gradients here, there are no gradients here, there are no gradients here, so we assume 2D. Okay? Any question? Again, also, experiments and simulation. Now, another thing. This reasonable validation. As a reviewer, when a paper from numerical studies came with two perfect lines, experimental and numerical, it smells. It's usually you have 5–10% of deviations. Okay, that's life. Can you, as an engineer, deal with that or not? With these 10%? For the purpose of your research, can you deal with these 5–10% or not? Even CFD has 5–10% deviation. Sometimes more. Okay? Any question? Good. Now, tomorrow we will do the optimization part. Yes, because if we start today, well, maybe we can I can explain you the concept of that. So basically, I will explain you the concept of optimization with another case study. Okay? The case study I will explain to you, it's something I have recently patented, okay? It's a new system that we have developed that is able to move PCM inside the wall. So now PCM technology has one big limitation, that it usually let me